Let's talk about Project 6, Lesson 26. So, we're given the information that Ronnie is scheduling a chess tournament in which each player plays every other player once. And he creates a table and finds that each new player adds more games to the tournament, and this forms an arithmetic sequence. So we're going to answer these Lesson 26 questions based on that chess tournament. So imagine that Ronnie has made a table that outlines how many people are in the tournament and how many games must be played so that each person plays every other person one time. So this column represents the number of players, and this column represents the number of games. So if you only have one player, well, that's not enough to play a game, so there are 0 games. If you have 2 players, for each player to play all the players, that only requires 1 game, right? Because there's 2 people. If you have 3 players and each one needs to play each other player once, that gives you 3 games. 4 players requires 6 games, 5 players requires 10 games, and so on. So our question is, how many games must be played when 7 players are in the tournament? So we have information up to 5, and we need to fill in the information for 6 and 7. So it helps to observe the patterns going on in this table. We can look at patterns by examining the difference between one item to the next. So what do I mean by that? For example, if I'm looking at the way the number of players grows, well, each time it's just incremented by 1, right? We're adding 1 player at a time. So I can see that the first difference is a constant number. It's 1. What about if I look at the games column? The difference between 0 and 1 is 1. The difference between 1 and 3 is 2. The difference between 3 and 6 is 3. 6 and 10 is a difference of 4, right? So we can see that on the left-hand side, the number of players for every new entry, the number of players grows by 1. Each time you add a player, we can see that you add 1 more than the number of games you added last time, right? So it's kind of a weird way to explain that, but again, our pattern is that we're adding 1 more player each time, and then our games increments by 1 more. So if I had to fill in the row 6, if I had 6 players, I know that to go from 5 to 6, I'm just going to add 1, right? What am I going to do to go from 10 to the next number? What's the number I'm going to add to figure out the number of games it takes for 6 players to be able to play each other once? Once you have the number of games for 6 players, you can build onto that one last time. Obviously, once again, on the left-hand side, I add 1 more time to get to 7. And I'll have to add something on the right-hand side to get my final number of games. So again, think about the differences, the constant differences or the first differences that are occurring in this table. Now for your second question, you're given 4 explicit rules, and you're asked to select the explicit rule for the sequence of tournament games. So we're trying to figure out an explicit rule that describes this situation that's happening in the table. So once again, I say examine kind of the information happening in the table. So we already know that to go from the number of games, 1 entry to the next, first we start by adding 1. Then we add 2 to get to the next entry. We add 3 to get to the entry after that. We add 4 to get to the entry after that. So each time we're incrementing the number of games we're adding on by 1, right? It's just counting numbers. 1, 2, 3, 4. Stands to reason that the next number we'll get by adding a 5, right? So those are called first differences, right? I took my original data set, I found the differences from each set of consecutive numbers, and those are my first differences. But I can also examine the differences between the differences, right? And I call that second differences. So the difference between 1 and 2 is 1, the difference between 2 and 3 is 1, the difference between 3 and 4 is 1, right? And I call those my second differences. So again, first differences are found by taking the actual data set and calculating the differences. Remember, difference always means subtraction. So my first differences happen from the original data set. Now I take those first differences and I find the differences between them. Those are my second differences. And notice that this is a constant number. It's just 1 over and over and over again. According to our lesson, if I have constant second differences, that means I have a quadratic pattern happening. So when you're looking at the explicit rules they've listed for you, that means it would be helpful to start by examining one of the ones that has a quadratic in it. Okay? Your answer is not going to be something that only has a first degree variable. It's going to have a second degree variable. So that'll save you some time in kind of checking into the numbers. So the answers that you are given to choose from, only 2 of them have quadratic terms in them. So from there I would just say, plug the numbers into the term and see which one gives you the pattern that you're expecting. Okay, so the n is going to be the number of games. So that's what you're plugging in. And when you plug in 1 for n, your answer should be 0. When you plug in 2 for n, your answer should be 1. When you plug in 3 for n, your answer should be 3. When you plug in 4, it should spit out a 6. And when you plug in 5, it should spit out a 10. That's how you'll know that you've selected the correct quadratic pattern. Okay. So question 3. What would the new explicit rule be if each player played every other player twice? Okay. So in the last question, we selected our explicit rule just for the original idea of each player playing everyone else one time. And we selected our explicit rule. So keep your last answer handy. And we're asked what would happen to this rule if each player played every other player twice. And if you look at this table, this is describing our new data, right? So still 1 player isn't enough to play any games. 2 players is a difference of 1, right? Just as before, we've got our table. But what does it mean if each player had to play each other twice? Okay, so rather than 2 people playing each other once, I'd have to multiply that 1 by a 2. Instead of 3 games, I'd have to have 6 games. Instead of 6 games, I'd have to have 12 games. Instead of 10, I'd have to have 20. So I have to multiply the number of games by 2. And think about what would happen to your explicit rule. Would I just need to multiply it by 2 to get my new one? Would I need to do something else? And of course, remember that you can always just take the information you got from the last question, consider what you've been told here, and you can still do it by kind of trial and error and process of elimination. Again, plug in your n's, make sure it spits out the right number at you. So in this case, 1 should still spit out a 0, but if you plug in 2 for n, these are your n's, remember. If you plug in 2 for n, you should get a 2 back. If you plug in 3 for n, you should get a 6 back. If you plug in 4 for n, you should get a 12 back, and so on. Question 4. Which of the following is a recursive rule for the original sequence? Okay, so we're back to our original sequence, so the difference between these is going to grow by 1 each time, so we already know that. We know that the difference between these is just a constant 1. So, I need to define a recursive rule for this. So right away, recognize the difference between a recursive and an explicit rule. Okay? So when I have an explicit rule, all I need to know is my n, right? And I just plug in my n and I listen to the rule and it tells me my term, my a sub n. When it comes to recursion, you have to know something about the terms. You have to have some piece of information. So often, in order to get a sub n, you often have to know a sub n minus 1, right? So again, explicit rule only relies on asking, well, which term are you looking for? What's n? What's the number? What's the term number that you want? And you can construct the number from that. When it comes to a recursive rule, you have to rely on information that you already know about the terms in the sequence to define the next one. So if I tried to figure out a sub n but I had no idea what the other terms in the sequence were, I wouldn't be able to do anything. Okay, so again, just looking at the answer choices that you have, not all of those answer choices even reflect a true recursive rule. So consider that first. And then again, from there, I would look at the remaining rules that are recursive and use your gut and decide which one kind of looks like it would display the proper information of what's going on here, and just plug in your numbers and see what happens. So in this case, we're plugging in, the rule could maybe demand that you plug in n, it could demand that you plug in a sub n minus 1. So let's take a look at what that would look like. So if I picked a recursive rule and I wanted to check it out and see if it was the right one, here's what I would have to do. So I'm just going to use a sub n equals a sub n minus 1 plus n as an example. Okay, I am not claiming that this is the correct answer. Let's take a look at what happens. So I'm being told that this term, a sub n, is found by taking the prior term, which is a sub n minus 1, and adding n to it. So I can select any of these. Let's say I want to double check this row. So these are my n's. In this case, I'm dealing with n equals 2. So this is my specific n, which makes this a sub n, and makes this a sub n minus 1, okay? Because n is kind of my index here. It's keeping count of which term I'm looking at. So, if I want to double check and see if this recursive rule correctly identifies what's happening in this table, here's what I would do. I need to check if my statement is true. So this is claiming that if I take a sub n, which is 1, so I'm saying 1 is equal to a sub n minus 1, meaning the term before it, which is 0, plus n, and in this case n is 2. So is it true that 1 equals 2? No. So this is not the correct rule. This is not the correct rule. Let's do one more example. So what if I wanted to, and I'll even use a different row just so we get an idea here. What if I wanted to see, and this time I'll just make up a rule. So let's say I had the rule a sub n equals a sub n minus 1 plus n plus 2n. So let's pretend that was our rule, and obviously this is the wrong answer. I just made this up. So I want to double check and see if this rule correctly describes my table. And this time I'm going to use this row. By using this row, what I'm saying is that n equals 3 and a sub n equals 3. Remember that a sub n minus 1 describes the term before. So this means that a sub n minus 1 equals 1. Okay? So according to this, a sub n, which is 3, is equal to a sub n minus 1, which is 1, plus 2 times n is 3. So that means I'm claiming that 3 is equal to 7. Is this true? No. So this is not the correct recursive rule for this. So as you can see, you would go through, double check your rules, and don't just double check one row. So just because had this proven true for this row doesn't mean I have the correct rule. So I would recommend double checking maybe 2 or 3 rows and make sure your rule works for each of them before deciding that you have the correct one.